Once again, welcome back. And today, last lecture we did reflection at the spherical surfaces, the various mirrors, the we call concave and the convex, etc., etc. Okay, and the formation of the images. Now today we will take up refraction. Refraction, which follows Snell's laws, and there is something called refractive index, and this reads refractive index of medium 2 with respect to medium 1. This is equal to sin I upon sin r, where I and r are the angles of incidence and refraction respectively. Okay. So refraction takes place when the ray of light travels from one transparent medium to another transparent medium. Of course, at the interface there is partial reflection and partial transmission, which is called refraction. Okay. If we have a normal incidence as shown over here, okay, then part of the ray is reflected back in the same direction, part of it is transmitted. Okay. But here, the angle that the rays make with the normal, they are 0, and we cannot apply this formula sin I upon sin r in this case. Okay. So for that we have to go to oblique incidence, in which the angle of refraction is not equal to angle of incidence. So there are two things that happen. That angle of refraction can be greater than angle of incidence. That is when we move from a denser medium to a rarer medium. Or otherwise, this r is less than I when we move from rarer to denser medium, which has been shown over here. Refractive index, of course, we have defined, like I said, mu21 is sin I upon sin r. But any symbol like that, mu12 is often written as 1 here and 2 here in some of the texts, particularly the old texts. Okay, but all the time we'll take this as mu21. The refractive index of medium 2 with respect to medium 1. Okay. Now look here. I have tried to draw the case of a denser medium to rarer medium. The ray of light, incident ray of light, is coming like this. This is angle of incidence, and then there is partial reflection, which is shown by double arrows. And here is the deviation, that you can say that in this case the ray of light bends away from the normal. Okay, nn dash is the normal. Okay. Now one thing at the beginning I must tell you, that if the ray of light were coming like this, when the angle of incidence becomes equal to I over here and angle of refraction r over here, in that case this will go like this. And similarly in the other case, where the entry is from rarer to denser medium, when the ray of light is bending towards the normal, okay, and r is less than I, the same kind of a incidence. Okay. So in this case it goes towards the normal, but the reverse, when it comes from denser to rarer medium, you can see that these red arrows, they retrace back this. This is one of the properties associated with ray optics. Okay. Now, according to this, When this angle becomes equal to this angle and this angle becomes equal to this angle, in the case of the reverse thing, then we get mu21 multiplied by mu12, okay, and this is equal to 1, that is mu21 is equal to 1 upon mu21, mu12, and mu12 is equal to 1 upon mu21. We also find that this is equal to velocity of light in first medium divided by the velocity of light in second medium. Now, the denser and rarer these words should be specified, and you see that the optical density and the mass density got to be distinguished, because sometimes for the same material the mass density is less than another material and optical density is more than that for the. So these things should be taken into consideration. For example, the mass density of turpentine with respect to water is less, but the optical density is more. So that is one example, and there are several examples which you can search in the textbooks. Now, here I am taking what is called the lateral shift. I have a glass slab, it is put in the air, and we have the incident ray which is shown over here. Naturally, the glass is denser as compared to air, and therefore it will bend towards the normal. I again draw a normal when it reaches this face, this interface, then of course this will be, it has been shown a bit different, but it will be diverged and it will bend away from the normal. Okay. Now, forget about my poor drawing, but the ray which is now extended as if it were coming without the presence of the glass slab, it would have gone like this, from air to air. But this one you can see that there is a shift, okay. This is parallel to this, this is parallel to this, okay. So there is a lateral shift, and it happens in the case of refraction. Next we are going to talk about the apparent depth, okay, and that particularly in the case of if it is in this glass and there is an object which has been put over here, then it will appear to be somewhere over here, the depth will be lesser. Or if it is water, okay, and then this is the apparent depth of the object. So if there is an object over here, for example, and if there is a face or anything with which you can, then it will appear to be, the depth will appear to be increased. Okay, so this thing we take next. So let us extend that as an application to the case where we have a water tank and there is some object which is lying at the bottom of the it's not necessary that this should be at the bottom, it could be anywhere, but what happens is that instead of looking at this depth, the eye sees that it is at a higher depth. The figure has been exaggerated, okay, I have just tried to convey the meaning. Look here, what happens? If I have our eyes fixed in the normal direction, near normal direction, then there are two set of rays, okay. This is one which refracted and this is another one, and they are collected by the eye over here, okay, and we see as if these rays which are coming to the eye, they are apparently coming from point O dash, which is the apparent depth, at a depth h1, okay, and the actual depth is h2 over here. Similarly, this is at the incidence when the eye is somewhere over here, I've just exaggerated that, and we normally have to exaggerate. Here, now I have the object here and the apparent image of the object which visible by the eye. Okay, when the eye is here, then we take another set of rays, okay, and that is, this is one ray and the other ray, and both of them are moving from a denser medium to a rarer medium. They bend away from the normal and they enter the eye over here, and the eye is able to see this at O dash, located at O dash. Okay, so that is it, and with the help of the geometry that is there, it's when you draw it on the paper, you can show that the mu of water with respect to air is equal to H2 upon H1, and the mu of air with respect to water is equal to H1 upon H2. These things you can show because you have done it in your high school classes. Another application of refraction is what we see in the morning as Suryodaya, and in the evening as Suryast, when the sun is coming. This is the horizon, and there is some observer over here. I have not made that earth part. Okay, so when the sun rays, they enter into the atmosphere, then they bend in such a way that the curvature is such to our eyes that if we look at the direction, then the sun appears to be over here. The sun is already below the horizon in the morning, but it appears to us as if it has risen, and in the evening it is otherwise. When this has gone over here, still you can see that the sun has not set. There is no Suryast, what we call in Hindi. This is one thing. The other observation, at the time of the sunrise or sunset, the sun appears to be of oval shape. Okay, because sun is a big object, and if different parts, then instead of being a perfect sphere, or what we can see basically is a circular shape, it is rather an oval thing, and therefore we look at the sun, that is the value of this shape. Okay, one thing I forgot before, then the Snell's laws. One is this thing, sin I upon sin r. The other is that the incident ray, the refracted ray, and the normal, they lie in the same plane, just like in the case of the deflection. Next we talk about a beautiful phenomenon which is called total internal reflection, TIR. Okay. Look here. We have a denser medium and a rarer medium. Okay. Maybe glass and water. Glass and air, or water and air. Doesn't matter. Now let's see what happens. This is the interface, the denser to rarer interface, and if there is a ray of light which is going along the normal, it will proceed in the same direction. Okay, maybe partially there might be a reflection into it. Okay, so there is a kind of a partial reflection which is also possible. Now let us take this point under consideration. This is exactly what will happen, that the incident ray after refraction, it will bend away from the normal. Okay. And we can apply Snell's law. Mu is equal to sin I upon sin r, okay, and that will turn out to be less than 1. Okay. Now let us shift this point where the ray is coming to the right. There will be a position when the ray of light which is coming from here will go at the kind of a grazing incidence, okay, and the angle here, the angle of refraction will become equal to 90 degrees. Okay. So in that case, mu21 can be written as sine of this angle I have just taken as IC, okay, and we'll get a relation like this. Sine of IC divided by sine of 90 degrees is equal to 1, and therefore it is equal to sine of IC. So IC becomes equal to sine inverse of mu21. Okay. Now beyond that, if we shift it a little further, then I have shown it in an exaggerated position, and that is now when the incident angle of incidence is greater than IC, then what happens is that the ray is reflected back in the medium, okay, and you can see that this is a reflection inside the denser medium. So this is called total internal reflection. Okay. You can see that if this denser medium body is very long, then a similar thing will happen at this edge, and then again at this edge, and again, and the ray of light which is having information about the point A will carry on through process of internal reflection, and this is exactly what happens in fiber optical communication. Okay, in fiber optical communication, the rays go like this, and without a loss of energy at all. Okay, through any reflection or scattering or anything. So normally it is a very poor loss or very good communication, and the information with whatever kind of an information is there modulated upon this, that goes in the fiber optical cables. Okay. Now, just to enumerate, I am giving you the various indices for the mu value of the material with respect to air and the corresponding IC values. So you can see that for water it's 1.33, okay, or 4/3. Ground glass, okay, which is without lead, or low refractive index glass, okay, this is 1.52, and the corresponding value here is 41.14, here it is 48.75, 1.62, 37.31, 2.41 in the case of diamond. Okay, and that's why the diamond sparkles, because the light is reflected from the various edges, edge faces of the diamond, and it looks very brilliant. Okay. So this is because of the total internal reflection. Two more phenomena which I am not dealing in detail. They are called mirage and looming. Mirage normally happens at very hot times when the air near the surface is rarefied. Okay, and you can see that it appears that there is the image, inverted image of the objects, and people think that it often happens when you are traveling on a hot road, then it is seen as if there is water ahead. But as our car goes ahead, and that also goes ahead and ahead. Okay. And this is called, this mirage is called, in Urdu we call it sarab, and in Hindi we call mrig marichika. These things have been dealt in class 9th, etc. And that's why I am leaving it. But looming is a very interesting phenomenon. And that happens at the seashores. And actually, the ships and the boats which are coming towards, particularly for the fishermen, okay, then it appears that they have come, and you calculate that, well, when they are visible, then it appears to you that they will come, for example, in 1 hour. But even when 1.5 hours has been spent, they are still far away. That is also because of the diffractive index profile. Because near the water, the refracting index is more, and on the upper side is less. So that is called a phenomenon of looming, which is kind of reverse of the phenomenon of mrig marichika, sarab, okay, etc. Okay. Another thing, which again I am not going to draw things out for you, because books are good, giving very nice drawings and they are very simple to understand, and you can do it in a 10 minutes time, is the application of total internal reflection in specially designed prisms. What they do, they will bend the ray like this, okay, so there is bending in 90 degrees, or they will bend the rays, are coming back, and they will trace back the rays in the opposite direction with the phenomenon of total internal reflection. And the same logic can be extended to invert an image. For example, if the image is the object is like this, okay, and then you can find the object in the inverted image B dash, A dash, the size is the same. Also, there is no loss in the information contained in the original object, and that we obtain in the image. So I leave you here, and I will rather delve myself into what is very interesting, and that is the spherical surfaces, okay, lenses, etc. in the next lecture. Thank you very much for now.